Hi guys, this is our last lesson of the chapter, lesson 8-9, and it is called perfect squares. We're going to talk about factoring, a special case situation. We covered this in lesson 8-4, where we actually were finding a pattern and using it to multiply our binomials into a trinomial. And the special case situation was this. We had, I'll just write it like this, a squared plus 2ab plus b squared equals a plus b times a plus b, which is the same thing as a plus b squared. And then sometimes we saw it like this, a squared minus 2ab plus b squared equals a minus b, and a minus b, which is the same thing as a minus b squared. Unlike lesson 8-8, where we need to be able to recognize a difference of two squares in order to be able to factor that pattern, this one will work the good old way that we did in lesson 8-7, where we do the AC factoring. So recognizing the pattern in this situation can be very helpful and speed you up, but it's also not entirely necessary. So let me show you some examples. If I have 4y squared plus 12y plus 9, I can ask myself some questions. Number one, is the first term a perfect square? In this case, 4y squared is the same as 2y times 2y, so yes. Okay, number two, is the last term a perfect square? In this case, 9 equals 3 times 3, so yes, it is. And the third question, is the middle term equal to what we would call 2ab? So in other words, is it 4y squared times we need the excuse me, we're going to need the square roots of those, times 9 times 2. We need 2y times 3 and then times 2. So that would be the 2ab. 2ab. It's not 2a squared b squared, it's 2ab. And so that would be 6y, double that would be 12y. And is the middle term 12y? Yes, it is. So if you answer yes to all these questions, this is a perfect square trinomial, and I can factor it into this. So all I have to do is get the square root of the first term plus the square root of the last term. And I would be able to see that this worked if I checked it with FOIL. And you can see where that saved me writing out the whole process. But if you didn't see it, you wouldn't die on this one. You would just do more work. And 3 times 3 is 9. We put that together. We have it. All right, let's look at another one. 9x squared minus 6x plus 4. You can look at the questions in your notes there that we just wrote down. Is the first term a perfect square? 9x squared? Yes, it is. That would be 3x squared. Is the last term a perfect square? Yes, it is. That would be 2 squared would be 4. And is the middle term equal to 2ab? So in this case, 2ab would be 2 times 3x times 2, which equals 12. Let's see, I probably have to have a negative in there. I would need a negative because of the pattern with negatives, but that's okay. I get 12x here, and that does not, and negative 12x, even if I count for that negative, does not equal 6x. So this would be not a perfect square trinomial. I would need to factor this a different way if it is factorable at all. All right. So here is a little summary of factoring methods, okay? This is pretty important. So step 1, factor out the greatest common factor. Any common factors, they need to come out. Step 2, check for a difference of squares. That's the most important one. Or a perfect square trinomial, if you can catch that. That one's not as critical. You'll just be doing more work if you don't. And 3, apply factoring patterns. So you're going to either do the factoring pattern for x squared plus bx plus c, or you're going to do AC factoring if there's a number that starts it instead of 1. And we won't write out all the different things. Or if you can't do that, you can factor by grouping and that is especially if you see 4 terms. All right, so here's another example. This is example 2. We have 5x squared minus 80. Okay, step 1, I just have to see if there's a common factor, and there is. There's a common 5. It's going to leave behind x squared minus 16, right? And now I see step 2, check for difference of squares. This is where I see the difference of squares. And so I'm going to have 5 times x minus 4 and x plus 4. All right. 4 is a perfect square, but x is not. So we'll be finished at this step. All right, here's another example. And feel free to pause and try these yourself until you get stuck or you've finished, and then start the video back up. All right, do we have a common factor here? It wants to look like a common factor, but I don't think so. We don't have a perfect difference of squares. It's not a perfect square trinomial because that's not a perfect square. And so we're just going to need to factor this the good old-fashioned hard way, because we have an A and a C. So we're going to do 9 times 35 is 315. And we take a deep breath because that looks intimidating, doesn't it? Use a calculator to help me grab some factors. Six go in there. Nope. 7. Yes. 8. Nope. 9, yes. Keeping my eye, since it's negative, 9 times negative 35 is negative. I'm going to need one number to be negative and one number to be positive. I'm adding together to get a negative 6, so my big numbers are all going to be negative. And I haven't gotten numbers that are close enough together to go in there yet. 12 doesn't work. That's maybe 15. Yeah, I've skipped a couple, and it won't matter as long as I find the ones that work. Okay, that one looks like that's going to work right there. So if you want to save yourself a little time, you can stop as soon as you see the ones that actually work. Okay, now I need to rewrite 9x squared minus 21x plus 15x. I was strategic there because I don't like the minus in the middle. Minus 35. I'm going to factor by grouping now. Parentheses go on these pairs. Common factor in the front here is a 3x. That leaves behind 3x minus 7. Common factor here is going to be a 5 times 3 is 15, just a 5, looks like. That'll leave behind 3x minus 7. Use the distributive property to check yourself at any point here. Common factor, 3x minus 7. And then look at the pink. What's left behind is 3x plus 5. And I have this factored. And it is finished. All right. How do I solve an equation with perfect squares? Here we go. 9x squared minus 48x equals negative 64. Whenever I want to use any kind of factoring for solving, I want things to equal 0 because I'm looking for roots and zeros and all that good stuff. So I'm actually going to add 64 to both sides. 9x squared minus 48x plus 64 equals 0. I don't think that's actually a common factor happening, but it is yelling at me that maybe something's going on with these bigger numbers. 3x squared is a perfect square, or 9x squared is a perfect square, it would be 3x. 64 is a perfect square, it would be 8. And if I do 3x times 8 times 2, I will get 48x in the middle. So I can actually factor this into 3x minus 8 squared. And at this point you can check yourself with FOIL if you want. And seriously, if I'd done AC factoring, I would end up with the same answer. It's just big, right? 9 times 64 gives me a big number to factor. In this case, I have 3x minus 8 equals 0. That's happening twice, so I don't really need to write it out twice. It's happening for kind of a fun reason. I'll show you in just a second. X equals 8/3. 8/3 is close to 3, but not quite. And what is actually happening in this situation, whenever I have a perfect square, I'm always looking for those two answers, but sometimes, let's say this is where 8/3 is, sometimes the parabola just kisses the x-axis and goes back up. It just touches in one spot. It doesn't actually dip down far enough to cross twice, and it only touches once. That's one of these situations, a perfect square binomial. We only have one root because there's your root. All right, let me show you one more example. We actually want to talk about this square root property here because it's another technique for solving equations here. So if I have a square root, I can do something like this. It's maybe just as easy to show you with an example. X squared equals 25. if x squared equals 25, I can actually square root both sides to solve it. I know that x times x equals 25, and 25 is 5 times 5, right? And so the square root of x squared is x, and the square root of 25 is 5. Now, watch out. We are still looking for two answers when we have squareds, and there is another answer. It also equals -5 times -5. So I need to catch both of those. This is plus or minus 5. On the graph, my parabola is actually doing this. Sorry, I didn't really cross there very well. But we're looking for both of those, right? And so let's look at an example. This is example 4 for today. We have y minus 6 squared equals 81. This thing is squared. And so actually, I can square root both sides, and because 81 is a perfect square, this is a smart way to do this. So I'm going to square root this whole thing, and I'm going to square root this thing. And the square root of y minus 6 squared, since it's y minus 6 times y minus 6, the square root is just y minus 6, okay? And the square root of 81 is 9, but 9 times 9 equals 81, and -9 times -9 equals 81. So it's going to be actually plus or minus 9. That means that I actually need to solve two things. This makes sense because I'm still dealing with things that have squareds on them, which means I'm still looking for more than one root. So I have to actually solve y minus 6 equals 9, and I have to solve y minus 6 equals -9. So let's add 6 to both sides here. I get y equals 15. And let's add 6 to both sides here, and I get y equals a -3. So watch out they don't match. But I did find both of those roots, the two places where we're going to cross the x-axis. All right, I think this is probably getting a little long, so I'm actually going to stop there. But you're going to be working some examples in ALEX, and send me your topics if you get to some ones that you're having trouble with. Love to help.